Hello everyone, today we'll talk about the problem largest rectangle in histogram. We're given an array of integers representing bars of certain heights, and we want to say what is the largest contiguous rectangle that can be created within those bars. So here the answer is 10, because we can fit a rectangle of size 10 within it. And we could also fit a rectangle here of area 8, or here of area 6, which is the same as this vertical bar, but 10 is the best. Let's start by talking about a quadratic time solution to this problem, and later we'll see how we can optimize it to linear time and be satisfied with solving this problem. Let's say we're looking currently at a new bar. Let's say we're going from left to right. Now that bar can be our largest rectangle, but maybe the next bar to the left can also be included in that rectangle. So what we have to do is to now remember that our rectangle is smaller. It has to be the height of the next bar, but now it's wider by 1, so maybe that's the best result. And then we see another bar to the left, so we still maintain the same height, and maybe now this with 3 rectangle is the answer. Then we see here a bar, maybe this with 4 rectangle is the answer, and so on. If we do that for every bar, so we start at every bar and try to extend it to the left, then we will find the rectangle of the maximum area at some point, so we'll have the answer in quadratic time. And the key to optimizing this solution is to notice that what we're doing here is this staircase pattern, that when we encounter a smaller bar, then our height drops to the height of that bar and stays there. So essentially we will have, when it comes to rectangles, we see a pattern like this, right? So we always look at rectangles like those. So the only interesting portions are those portions where the height changes, because for instance this big rectangle will be here, then the height will change. Then the height, when it drops, we'll think about the rectangle here, right? And so on. And we don't care about things that are above the staircase. And if we can maintain some data structure or look at the problem in a certain way such that we can actually simulate using this staircase pattern, then we can solve the problem in linear time. And indeed it's possible. What we're going to do is we'll be maintaining the staircase, the points where the staircase changes, for every bar. And whenever we move to the next bar, we just have to update that staircase. And how do we update that staircase? Well, if the next bar, for instance, imagine that we're here, if the next bar is higher, then we add it to the staircase. And if the next bar is smaller, then we have to remove everything that's greater than it, so that the staircase becomes something like this. And along the way, when we remove them, we can update the result. Because for instance, when we remove this bar here, then we might say, okay, so maybe this is the solution. And then we remove this bar because it's too high, so maybe this whole thing is the solution, right? And to do that, we'll just maintain a stack of events, a stack of points with their x-coordinate and the height at that point. And by maintaining this stack, we can solve this problem in linear time. Let us see the code. Here we'll be maintaining the current staircase as a pair of position and height at that position. We'll put some dummy values so we don't have to check if it's ever empty. And we'll go through all the elements of our given list of heights, looking at its position and its height. And for as long as the previous element on the staircase has height that is not smaller than our current height, right? So it's too big, then we try to create a rectangle of that height. So that will be the width that rectangle can have times its height. We remove it from our staircase, and now we know that for any rectangle that will go through these coordinates, then its height is at most our current height, right? Because for everything to the right of us, since we have a height of h, we'll cover anything bigger than that to the left. And finally, when the next thing on the staircase is smaller than our height, we just have to add ourselves to the height, add our height to the staircase, starting at the appropriate time, which is either this very position or the last position, the most leftward position that we've removed. And then later, when we have a staircase, we also have to remove everything from the staircase and try to update the result based on it. So for instance, if this is the original array, then we would never remove anything from the staircase, and we now want to consider this rectangle, then this rectangle, then this rectangle, and so on. So it's this portion, and that is the only thing that's necessary to solve this problem.